Hello, I hope you're doing well. So today we're going to continue with the topic of identical particles, and we're going to study basically solids and the origin of their band structure. But in order to get to band structure study, we basically need to complete an analysis of two different models for solids. So let me share the screen to start. Okay, so yeah, we're going to talk about solids, which are the way we're going to conceptualize them are basically composed in atoms, by atoms. And we're going to assume that these atoms are in some sort of crystalline structure. And we'll have a name for that structure. We're going to call it a crystal lattice. So for these atoms, the outermost valence electrons basically are not completely bounded to the nuclei. So they can move around the solid, around this material. And when they move around the material, they feel the potentials of the different nuclei. So that's the way we understand basically electron transport in the solids. And we're going to consider basically the two simplest models for the electrons moving around the material. Um, the easiest one is basically think of it as an electron gas, which is the theory of Sommerfeld, in which what we're assuming is, well, we're basically discarding the potentials of attraction between the electron and the nuclei and the electron-electron repulsion. So it's moving around. And the only potential that the electrons feel is basically at the boundaries. So you have them as some sort of sets of free particles moving around the material and cannot escape it because they basically cannot exit the potential barrier at the boundaries. There is a second model, which we'll discuss on the next lecture, which is to still discard the repulsion between electrons, but what we'll now add to the analysis in that other lecture is basically attraction between electrons and nuclei. And again, the nuclei are soon fixed in the crystal lattice. And because they are fixed, the periodic, well, the potential that the nuclei generate over the electrons is periodic. And that is basically Bloch's theory. But that's for next lecture. Today, we'll focus on the free electron gas model in solids, which is the theory of Sommerfeld. And yeah, we'll study some features. Actually, we have to go into detail in terms of the mathematical solution of this model. There's some simplifications that do not take too much in terms of the generality of how applicable it is, but never mind, let's study. So basically, again, we are considering free electrons to be only affected at the boundaries. So no interaction with the nuclei or repulsion between electrons. And again, for sake of simplicity, we are just going to assume that the solid has a rectangular shape. That is to make the analysis or the mathematical analysis, particularly with respect to boundary conditions, simpler. So because the solid is rectangular, it has a length, width, and height, which is L(x), Ly, and Lc. And well, again, this is basically a 3D equivalent situation to the free particle inside a box, where you have an infinite potential at the boundaries. So it's basically the 3D analog of the infinite square well, but for this 3D rectangle. So the potential is defined like this. If you are inside or in the interior of the box, defined by 0L(x), 0Ly, 0Lc, the potential is zero, but at the boundaries and outside, the potential is infinity. So clearly it's the 3D equivalent of the infinite square well potential. And we kind of know from the beginning what to expect, at least qualitatively, right? I mean, basically free particles inside the box with a wave function vanishing at the boundaries. Uh, so let me add. And well, the reason we chose this shape for the solid is because the handling of boundary conditions is very simple. As you can anticipate, what will happen is that the problem is separable in each one of the dimensions x, y, z. So our domain is basically this cell. and we'll have the Schrodinger equation inside. So we know that the function will vanish at boundaries, but on the interior, yeah, you have the wave function modeled by Schrodinger equation, and you are expecting the variables to be separable. I mean, the kinetic energy, which is related to this Laplacian, is separable if you express it in terms of the coordinates x, y, z, and likewise the potential just for simplicity. So you propose a separable solution. You probably have seen this in PDEs before. So a function of x times a function of y times a function of z, and you plug in that proposed solution, which is separable in Schrodinger's equation, right? So again, this is, first of all, why the kinetic energy, which is this Laplacian, is separable for each one of the coordinates, right? Because it has this form. Second of all, the potential inside the box, which is what we care, since outside is infinity and the function or the wave function vanishes at the boundary, is zero. So we don't even need to take it in account. The way the potential will appear, indicating the force that doesn't let the particles exit the box, it's basically in the boundary conditions. So you plug in the proposed separable solution, which is over here, then kinetic energy, blah, 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 equal to the energy of this product function. And well, you apply each one of the summands of the Laplacian operator, but this is very easy because the function is separable, right? So when you apply second derivative with respect to x, the only term that carries derivatives is x, and you have x double prime, and then you have yc multiplying, and likewise for the other side, x double, well, xy double prime times c plus xyc double prime. And so the easiest way to basically show that this system is indeed separable is to divide by the product. Because, well, basically the terms that were not changed will disappear, and you'll only retain terms where you have a second derivative, of course, divided by the respective variable. So what you have by dividing by xyc, okay, this term is independent, so you have the energy, then yc disappear over here by the division, and you only have x double prime divided by x plus y double prime divided by y plus c double prime divided by c. So at this point, it's clear that the equation is separable because, well, it's the usual separation of variable arguments. I mean, this is a function of x, this is a function of y, this is a function of c. Um, this is a constant. Basically, by perturbing in one of the dimensions but keeping all the others, you can basically assume that each one of these summands is a constant. So what you have is that this energy is made of three separate individual energies, each one related to, say, the x variable, the y variable, and the c variable. But this term on the right side is constant. So you have simplified the problem by separation of variables, where now you only need to solve these ODEs with appropriate boundary conditions. And well, I mean, this is clearly a harmonic oscillator problem in each one of the dimensions, and you only need to apply boundary conditions to fully determine the solution. So of course, there's a way to simplify things by basically passing this constant to the other side and defining k as the square root of this object. The equation that you have is minus x double prime divided by x equal to kx squared, where kx is this constant. So this is equivalent to this formulation. And likewise for the equations for y and c. So, I mean, now it's completely clear that we have the harmonic oscillator problem, and these are terms related to the frequencies. So, well, yeah, I'm still not going to apply boundary conditions, but anyways, I mean, at this point, especially, you know, after we have defined these constants, we have sines and cosines. So that is the solution in each one of the dimensions. The question is how to determine the coefficients. And that is coming from the boundary conditions, because we know that the wave function should vanish at the boundaries. So these nodes, or this vanishing of the wave function, should imply that at 0 and Lx, for example, the x function will vanish. So if you plug in over here, the first condition x of 0 equals 0 makes this term vanish. This one cosine is 1. And so that means that bx is equal to 0. Now, without understanding, if you apply the second boundary condition, because you'll only have this function of x, that will mean that plugging in x equal to Lx, klx, Lx must be a multiple of pi so that the sign vanishes, because those are the points where the sign is 0. So that means that this product kx Lx is equal to nx pi, where nx belongs to the natural numbers. So of course we have labels, sub-indices to distinguish the natural numbers. The reason we can restrict to the natural numbers is, first of all, because n equals 0 would give you a trivial solution, because sine of 0 is 0. And then the negative n's are essentially equivalent to the positive ones by symmetry of the sine function. So basically you would carry a minus outside, and that's equivalent, and these coefficients are defined up to a phase. So we only focus in the positive ends. And the solution is equivalent for y and z. So this is determining, in terms of basically the boundary conditions, uh, the acceptable values for kx, so as in any boundary value problem. So at this point, we have found the separable solution, um, basically determined by some numbers, nx and y and nc, which will be our quantum numbers for this problem in a way. And so the last thing to determine is basically the normalization constant, but that's at the very end. The important thing is that we have realized that x, y, and z are all signs, that kx is equal to nx pi divided by lx, likewise for ky and kc. And well, I mean, clearly you're satisfying the boundary condition, because when you get to Lx, this will be a multiple of pi, and then the sign there is 0, and likewise. So this constant is coming from normalization. I'll let you check that. But we have determined the function up to a phase. Again, that's always what happens. And well, because we have determined the kx and, well, the k's, we have also found the energies, right? Because we made that definition of the kx in terms of the energies, and we can likewise express the energies in terms of these coefficients k's. So the equivalent expression is this one, which is not surprising because this is accounting for the kinetic energy for each one of the modes, if you want to think about it. And substituting for kx equal to this, nx pi divided by lx, and so on. These are the individual energies that you get in each dimension. So finally, when you add them together, the energy, which is due to ex plus ey plus ec, just what you only need to do is to add the k's. They all have a factor of pi squared, which is outside, and then you have the different summands, and they are squared. So here, so I have a very silly type. Um, okay, so the factor of pi squared is outside. And well, let's see, what else am I missing to say? Well, yeah, we have defined the k vector, which is made of of components kx, ky, and kc. And well, the reason is because you can interpret basically this as the norm squared of this wave vector. And so this will define a crystal momentum space where basically if you define P as h bar k, this has dimensions of momentum. And clearly, basically at this point, if you reinterpret this with the h bar factor as p squared over 2m, this is indeed behaving like momentum and giving the associated kinetic energy. Um, so let's see. Yeah. So we have separable solutions, which are identified by the indices nx and y and z, and equivalently in wave vector k space by kx, ky, and kc, which is a rephrasal of what we have found before. Um, and yeah, I mean, the important point is basically our separable solutions are identified by the numbers nx and y and nc, or equivalent by the points kx, ky, and kc in the momentum space. So each one of these points is giving you a separable solution. Um, so basically, the solutions define the grid or a lattice in the wave vector k space. And I want to show an illustration, which is basically from Griffiths, where, I mean, yeah, these are basically the points that are representing each one of the stationary states that we found by means of separable solutions. So this is what we mean when we talk about k-space. And most importantly, because they are organized in a grid, what we can do is to associate to basically each solution a certain volume element in the k-space, you know? So we can identify each one of these volumes, and because, well, basically think that when you go from a cell to the neighboring one, you simply change one of these natural numbers by one. So going back to the illustration, let's say that you were here, right? And you go to the next one. So perhaps because this is the y direction, the natural number associated to y has changed, but you know, for x and c, you have remained the same, so it's okay. And so that means that you can define a volume associated to each solution. And that is basically given by the product of pi over Lx times pi over Ly times pi over Lc, which is pi cubed over b, where b is the volume, Lxay and Lc of the box. So um, you will see in a second why this is useful. So the nice thing, though, that you might notice is that there's essentially a Fourier relation between the position space and the wave vector space. And this is anticipating the sorts of Fourier relations that you know from position and momentum, although in this case it's crystal momentum, which is h bar k, typical of quantum problems. So, I mean, we're kind of like observing the quantum features, especially because we have assumed that we have the crystal structure, which makes convenient the rectangular domain. But never mind. I mean, that's fine. So let's see. Let's continue. Yeah. So, okay. So far, basically, because we have free particles or free electrons inside the box, and the only force that they feel is the one at the boundaries, we have considered the problem as if we had a single electron. It won't make too much difference when we consider many electrons, because we have discarded the interactions with between themselves. So we only need to basically add them, right, to consider the collective of electrons. In general, I mean, some features might continue, but some others might change. So we have n atoms, let's say, by assumption, where n is of the order of Avogadro's number, so that's a very large number. And each one of the atoms contributes, say, d free electrons, and d is a small number. So because we're thinking about the free electrons, right? So, I mean, it can take values, say, as 1, 2, or 3. And the important thing is that, okay, perhaps we're not defining a potential of repulsion between electrons, but what we know is that even if they are free particles inside the box, they are still identical fermions. And so Pauli exclusion principle still applies, and that way, basically, the presence of many electrons inside the box is felt. So that feature will indeed be included. So perhaps what we are not considering is a Coulombic repulsion potential between electrons yet. But we do have to consider that there are fermions and there is a Pauli exclusion principle governing the situation. And so if you remember, when we added the spin considerations, we said, okay, the electrons can be basically in the same special state, but they have to be distinguished by the spin. So that means that for any basically state or separable state that govern only the spatial part, you can have two electrons, right? Then that is because of spin considerations. You would basically, I mean, hand wavy way is to say, well, one of the electrons is spin up, the other is spin down, but the spatial part is basically the same for those two. So this is important because this indicates how the states are filled. Basically, each state defined by these quantum numbers is filled by two electrons. And then you also have to consider, in addition to Pauli exclusion principle, minimization of energy. So basically, we're going to fill the lowest energies, each one of these states with a given energy going from the lowest, putting two electrons in each one of the cases. So what we want to do is to basically count how many electrons we have on a given spherical shell, because energies are defined by the norm of k squared. So if we consider the volume in k space for each state instead of the number of electrons, because we'll essentially jump from uh, this lattice symmetry to spherical symmetry due to energy considerations in order to fill the states. So, okay, this is the form of the energy. It depends on k squared. We want to count this, knowing that the volume for each state is this one. And most importantly, and this is where I will go to my second slide. So this is the filling of in k space according to basically lowest to highest energies, since we have that A depends on k squared. And the way we're gonna basically consider the total energy is first figuring out the number of electrons that we have available. And then instead of counting over the, say, quantum numbers in x and y and nc, infer it by dividing the volume of this octant by the volume of each element. And of course, performing a sum, which is essentially going to be an integration over these shells. So first things first, because the quantum numbers are all positive, you can only consider the first octant. That is the only one that is giving you basically all coordinates of k non-negative. Second of all, we'll perform integration. But basically, this is the argument. So this is the volume of the octant, which is volume of a sphere divided by 8, where we have defined the Fermi energy. Wait, where was this? Perhaps I haven't defined it yet. Oh yeah, I have to mention something. So, well, so far I have mentioned that we are going to work only with the first octant because we have quantum natural numbers. Now, uh, we basically want the relation between the volume of an octant of a sphere of radius kf, which is basically limiting it's up to where we fill it, that we're going to define as kf. More precise definition will come in a second. And basically the number of states to be filled by our ND total free electrons. So that we know. I mean, this is something that we know, how many electrons we have. We also know how many states. And we know the volume. So we basically want to count how many electrons we have in the shell, which we'll perform by integration. We'll present the analysis in a second. And then we'll add the total energies. So what we have first is basically, this is the volume of a sphere of radius kf. and this is divided by 8 because we are considering the octant. Then what we have is the number of states, because above what you have is the number of electrons, but this is divided by 2 because you know that you can have occupancies from spin up, spin down. Now, this is multiplied by the volume occupied by an individual state, because this is reflecting by dividing by 2 the number of states. So basically, the volume of the total states for our problem of interest is equal to the volume of the octant of our sphere in the first quadrant. So far, so good. We're doing this analysis because this will define the radius of the sphere that we're considering over here, which is Kf. So by doing algebra, we're going to pass to the other side. So the radius of the sphere whose first octant is occupied by electrons filling the stationary states. Well, you can simplify. Basically, if you pass the 2 to the other side, you see that you have 8 divided by 8, so that will simplify. Then you have pi squared. Then basically, well, let's see, you don't have a factor of 3. Um, then you have pi and pi cubed, so you'll simplify on that too. And therefore, you can find that Kf is equal to the cubic root, excuse me, of the terms that survive, which is 3 pi squared nd over b. But if you think of nd over b as actually a density, because nd is the number of electrons, of free electrons, so that's why it's called free electron density, and then divided by b, which is the volume. So this is the number of free electrons in the position space, volume b equal to Lxl, y, and Lc. Plugging in this, what you have is that Kf is the cubic root of 3 pi squared times rho to the 1/3. And so, well, there's a name for this radius, and basically, and also for this sphere surface. So Fermi surface is the boundary that separates occupied and unoccupied states in K-space, as clearly it's happening right here. So check the Griffiths for the illustrations, because that's where I'm taking them from. And each shell in the K-space of thickness decay is basically of the following volume. So that also defines basically this as the Fermi energy. So once we have found the boundary that separates occupied and unoccupied states, the energy basically related to that surface is called the Fermi energy. So that's important. So this is why the K has a subindex F. So, well, you only have to plug in the result that you have over here. And this is the energy at basically this K squared, which is plugging in this result above. So now we want to calculate the total energy of the gas made of free electrons, and we'll do it by integration. So what we basically have to do is to account for the energies going from 0 to E kf, and counting the number of states and the available energy. So, well, let's do it by analyzing the shells. So shells as the ones that I have here. So each shell in the K space is of thickness dk in our basically volumetric analysis. And what we do is to take the volume of the shell. So this is the area, 4 pi k squared times the thickness of the shell. So this is a volume. We divide by 8 because we're working with the first octant. And then what we have over here is the simplification of this, 4/8. And well, the number of states in the shell is basically multiplying by 2 to account for spin occupation, is obtained by dividing the volume K space above by the volume of an individual state. So think about this for a second, right? So this is basically the volume of the shell of thickness dk. So we have it over here. Then we divide by the volume occupied by basically an individual state, but we haven't considered spin yet. So that's why we have the 2 over here. And So because we can have basically a state with the spin up and the other with the spin down, with still the same quantum numbers for the position part or the spatial wave part. So that's what we have. And if we do that computation, many things simplify. First of all, this factor of 2, then a pi as well. So that's why you have b jumping up, and then divided by pi squared, k squared dk, and this is just a substitution for b. Um, well, yeah, it's a dimensionless number because we're counting for the number of states, so that's good. I mean, I guess it's a sanity check. And each one of the states in the shell of thickness decay has this energy, right? Because that's precisely why we have done the analysis in terms of shells. What we're doing is basically counting the number of states with a given energy. And then what we're going to do to uh, amount for the total energy is to multiply each energy by the number of states in that energy. So that's what we're going to do over here. And if we consider basically a differential of energy associated to the shell of thickness decay, so that differential of energy is the energy at that shell times the number of states in the shell, which is what we're doing here, okay? So this is the energy, this is the number of states. If we do the computation, we get the simplification where this is of order k to the 4. And now we can actually consider the total energy contribution of all electron states because basically now that we have added some sort of density for the number of states with a given energy, we can perform an integration from 0 to the Fermi energy of the energies where they have been weighted by the number of states as above. And using this situation, some constants will come out. Basically, what we have to do is to integrate k4 over k, which will give you a k to f to the fifth power because the limits are kf and 0, and then a factor of 5. So what we also knew from before was that kf had this relation with the volume of a cubic root, and we can plug in that formula um, by basically substituting over this part. So that's why we have 5 over 3. And there's some simplification still going on because we have pi squared on this side and b, and they are inverse to the situation inside. So if you do that simplification, actually pi squared over b are to the 2/3. And well, you have taken the b, so 3 and d still remain with the power 5 over 3. So basically, there's an inverse relation between the total energy and the spatial volume. So that's important because by these considerations in terms of Pauli exclusion principle, because we can interpret this as basically the particles exerting some sort of quantum mechanical pressure over the walls in the following sense, that say, let's think that the volume of the box expands, right? So that would mean that there will be a loss in total energy. And that is estimated basically by differentials. So taking derivatives, the differential of the energy, you just apply your usual known differentiation rules. So that's why you have minus 2/3 because it's b, and then this, then b to the minus 1 times db. And so, I mean, if you reorganize the terms, basically what you have done is pick up a factor of minus 2/3. Uh, some part remains the same, which is accounting for E total. And then you have basically b minus 1 and then times db because it's a differential problem. So we can also interpret this that in this situation, when the box volume expands, this accounts for work done over the environment, where the differential of work is the pressure times the differential volume. So if you equate all these, basically the work done over the environment by applying this pressure over the walls, the differential of work is equal to minus the differential of total energy, which gives you this. And because we have the B on both sides, we can figure out the pressure, which is 2/3 of the total energy divided by the volume. And well, we can plug in this term over here. And well, accounting for the 2/3 by B. So well, we had a factor of 2 over here, so we can simplify, which is why you have 1 over 15. And most importantly, well, I mean, I guess the 3 and the pi squared can be simplified because you have basically 3 times 5 times pi squared. So that reduces the power of this to the 2/3 for 3 pi squared, and rho still keeps the 5/3. So basically, to finalize this section, we can interpret the results in the following form. So our solid, it's not that it doesn't collapse in this model, of course, because we have done many simplifications, right? But even with the simplifications we have done, the solid doesn't collapse. And so far, we have not considered internal pressure, or sorry, we have not considered the repulsion between electrons because we have neglected. So the internal pressure is coming actually from basically the Pauli exclusion principle. So no repulsion between electrons has been considered. No thermal motion has been considered yet. And so the internal pressure is actually coming from the quantum effects over fermionic particles, which is basically the Pauli exclusion principle where you must satisfy antisymmetry requirements for the total wave function. So, which in this case we have fermions, which are electrons. There is a name for this, which is sometimes called degeneracy pressure, but perhaps a more proper term would be to call it exclusion pressure, as Griffiths mentioned, because it's more accurate into where the pressure is coming from. But yeah, I mean, basically the summary of this part is that by applying Pauli exclusion principle, by antisymmetry requirements, have found a pressure that makes the solid to not collapse. And well, yeah, so far, so good for today. I will finalize the section by talking basically about the origin of the band structure of solids, but there we need to consider basically less simplifications. So that will come from the periodic potentials between the electrons and the nuclei and the related blocks theory. So I have used Griffiths for as reference for this topic. So if you want to continue your study on this. So I'll stop for today and communicate with you by email in a second. And well, I hope you have a nice weekend.